So now let's look at how to find the length of a curve. And the idea is this. So if I were to have a curve, let's just consider x squared, or f of x equals x squared. A nice little parabola. And I can consider 2 points on here. I could do distance formula between 2 points, but clearly for something that has a second derivative not equal to 0 or is curving, has curvature, the curve will be longer than the straight line. So I can't just do distance formula and get the length of a curve. But what we will do is start with distance formula and modify it to get there. So I'll write the formula first. So the length will equal the integral from a to b of the square root of 1 plus dy dx squared dx. But let's see how this came about. So I'll get to some examples afterwards, but here's the idea. If I have some curve, and I want to find the distance between 2 points on that curve. This is curved, so distance formula isn't perfect, but if I zoom way in and look at a small section of this curve, since this is differentiable, it will be locally linear, and in this region it'll look like a line. We know in our line, if I want to find the distance along a line, I can do delta x, delta y, and make a little right triangle and have this piece right here be sort of the change in my length from these 2 points. And so I can do a little bit of Pythagorean theorem and get that my change in the length squared will be approximately equal to my change in x squared plus my change in y squared. Approximately equal to, because if I take any positive or negative, any non-zero change in x and in y, if this one's second derivative is not 0, it'll be curved, and so the length, it won't make a perfect right triangle. But how we fix that is the following. Instead of taking these actual steps, we can take infinitesimally small steps, dl squared, and that will exactly equal dx squared plus dy squared, because on an infinitesimal level it is locally linear, so it behaves just like a line with a nice little right triangle. And now I can do a little bit of calculus, because I want to figure out what L is, so I'll take the integral of both sides. Or actually, let me do something else first. Let me get dl by itself, so I do square root first. And I'll get dl is equal to the square root of dx squared plus dy squared. I'll take the integral of both sides to get the L by itself, and I'll get L equals the integral from some starting value to some stopping value of the square root of dx squared plus dy squared. Now the problem here that you should all see is this doesn't look like our normal integrals. We don't have a dx or a dy sitting here to do our integral over. But what I can do is this. I can factor out a dx squared from in here and have the integral from a to b of the square root of dx squared times, and when I factor a dx out of here I get 1, when I factor a dx out of here, I get dy dx squared. And so you can see if I multiplied through, I get dx squared, like right here, and I get dy squared, like right here. But the square root of dx squared is just dx, so we end up exactly where we want to be, integral from a to b of the square root of 1 plus dy dx squared dx. So that's a little proof of why this is the formula for the length of a curve. So now all I need to do is see some examples at how this works. So for this first example, let's find the length of f of x equals sine x from x equals 2 to x equals 5. And just for reference, we know that sine is going to look like this. So starts at 0, 0, and I'll put a full period going this way and a full period going that way. And of course we don't have an algebra formula to find this, but we're trying to go from 2, which is going to be approximately here, to 5, which is going to be approximately here, and find the length along here. And so all I do is I find f prime, or find dy dx, which in this case will be cosine x, and then follow the formula. The length will be the integral of that sort of distance formula thing, integral from 2 to 5 of the square root of 1 plus cosine of x squared dx. One thing, or two things to point out here. First off, almost all of these will be very difficult to evaluate by hand, so pretty much everything I would expect to do would be either to write the integral being a problem or go to the calculator and get a numerical answer. There are some, once we get to parametric equations or vector equations, that I can somehow get a perfect square in here and it works nicely, but a lot of times this is just going to be a mess. Second thing here, a common mistake that I see showing up is kids will put in sine instead of cosine. Make sure you do take the derivative. And now I'll just go to a calculator and I'll write this in very carefully. So if you have one of the newer TI calculators or some that have a nicer, they have math print or something, it's easier, but if you're doing this you have to be very careful. So I'll do math 9 for fn int, and I have the square root, and it gives me another parentheses, 1 plus, and I'll type it in like this. I can actually avoid one set of parentheses, but I'm going to just type it in straight away. Cosine of x. I have to close off 2 parentheses for the cosine. Then I square the cosine, and I need to close off another parentheses for the square root, but no more parentheses because I need to put in that the variable is x, and I'm going from 2 up to 5. Now I can close off the final parentheses for the fn int. Let the calculator do some thinking, and I get that the length of the curve is approximately 3.70. Hold on, did I say that right? 3.670. Okay, a second example, and it works pretty much the same way. Only difference here is instead of having things in terms of x, I have them in terms of y. So this is going to be a cubic function. It's going to be turned sideways, so it's going to look something like this. So I'm not positive exactly where the axis is going to go in there, but something like this, and finding the length from 0 to 1. And so I do the same thing. I find the derivative, which is going to be 3y squared minus 3. And then I'll do the length of the curve is equal to the integral from 0 to 1 of 1 plus 3y squared minus 3 squared dy. Only difference really here is I have dy's instead of dx's. The variable, the independent variable is what's going to go here. It's actually pretty easy to get in. In the calculator, I have the choice to either do things in terms of y, so I could type it all in, math 9. I have the square root of 1 plus, and I need to open up with the parentheses. I could expand this, but that just is more opportunity to mess up, so I usually just like to put it in as is. And if I want to, I can type in 3 y squared minus 3, close the parentheses off for that, all squared, close the parentheses off for the square root, and the variable we are integrating over is y, and I'm going from 0 to 1, 2.296, or I could just do this with x's in there. That's a little bit easier because I can press this key to get x's in easily. So answer for that is 2.296 approximately. Hope that helped out. Comment below with any questions.